And you can see from the title, the big title, and therefore I don't have time to go into the details. I'm going to give you a brief concept of what we are doing at Monarch. So this work was mainly conducted by my PhD student and now research fellows, in collaboration with Professor Yang Nguyen from the University of Adelaide, who's here in the room. This is the content of my talk. So I'm going to start by highlighting several challenges related to internal erosion. And I'm going to show you how we using a numerical tool to provide some further insight into the micromechanics of the internal erosion process. And then how we're going to upscale the understanding to formulate a statistic model to describe the influence in internal erosion on the mechanical consequences of the soil. And finally, I'm going to show you how we're going to develop a computational model to predict a field scale application. So what is internal erosion? This is the CFD-DM simulation showing how the fire particle is transported through the pore of the large grains due to the seepage flows. And this is an example of internal erosion. And you can see this internal erosion is basically occurs at a very large, very small scale. And it's normally hidden undetected. The challenges associated with the internal erosion is, on one hand, it occurs at a very small scale. It would take months, years, or even decades to be able to detect the internal erosion. But at the same time, when the failure occurs, it will actually occur within a period of hours. And you can see, if you're looking at this diagram, there's a significant difference in terms of spatial scale and also temporal scale. Modeling this significant difference in terms of spatial and temporal scale is still a challenging task. So how are we going to develop a computational model to capture one of those effects? In order to develop a computational model, normally we require this in Rosen, and we require three key components that include acoustic modeling, basically describe the mechanical consequences of internal erosion. We need to looking at the mathematical model, basically the governing equation. Within this community, you see a lot of Navier-Stokes equations to describe the fluid flows. But for us, we need to also looking at how the fluid flow and mechanical coupling. So this is something we will be looking at. And then we need a numerical tool to basically solving those governing equations in a very efficient manner to cover what we discussed in terms of the different in terms of the temporal scales. So I'll start with the acoustic modeling part. So this is how we normally looking at the internal erosion in the experiments. So on the left-hand side, you see the standard tri-tier setup to investigate the internal erosion, the effects of the mass loss on the mechanical consequences of the specimen. The procedure is here. We start having the soil specimen, and then we confine the soil specimen. Some actually even go further by subject the soil specimen to a pre-shear pressure. And then we subject the soil specimen to internal erosion and measure how mass loss with different quantities of the hydraulic gradient. And then after that, once the air sample was eroded, we share the soil specimen. So basically, we're looking at how the internal, the mass loss affecting the mechanical behavior of the material. So this is a common practice. We're looking at the influence of mass loss due to internal erosion on the soil specimen. But this is the issue. There's a couple of research conducted in the literature, and you can see that the soil specimen, when we prepare, is highly homogeneous. But one is actually being eroded, and you can see the sample become highly non-homogeneous. So basically, because the sample has become highly non-homogeneous, it's no longer considered as a representative volume element. So if you actually share this soil specimen, you're actually looking at a boundary value problem rather than the representative volume element. So this is the issue that we have with the experiments, and we need to actually find a way to overcome this challenge. But option, the other option we could do is to looking at using a numerical tool to actually investigate this internal erosion process and how the mass loss affect the mechanical consequences of the sample. We can use the CFD-DM simulation. This is one of the work done by my PhD student, fully coupled CFD-DM simulation at different scale, and you see how the mass loss transport through the whole system. The good thing of this sort of approach is that it actually provides the full access into the information of how the hydraulic and mechanical property affecting the mechanical behavior of soil specimen, but they're still having some similar issue like after the sample being eroded, it's no longer homogeneous. The other option we could do is to use poor DEM simulation and try to simulate the erosion process in a way that it actually make the sample remain more or less homogeneous after the mud load occurs. So for example, in this case, we create a sample and then we actually using some certain condition like looking at the force distribution and gradually reduce the mass of the small particle which have less force acting on it. And with this approach, we can actually create a sample that is more or less homogeneous after being eroded. So we're using this approach looking at the mechanical behavior of eroded soil specimen. And this is the setup. This is soil specimen. We look at the gap-graded soil. This is the process. We follow the experimental process. We subject the specimen to the initial confinings and then we erode the sample by gradually remove the particle, and then we shear the soil specimen. So you can see this is the typical behavior of three different types of granular materials, loose, medium, and dense. And you can see this sort of the result produced by DEM simulation generates a very sort of the standard behavior of a granular material. What we are very interested in is looking at how the pre-shearing stress ratio affecting the mechanical behavior of a material. Because looking at the literature in terms of internal erosion, we're actually seeing a quite interesting report that if the sample is subjected to low pre-shearing stress ratio, the sample was able to stable after being eroded. But if you actually load the sample to relatively high pre-shearing stress ratio and then you erode the sample, it will fail at this location. So we want to actually understand this mechanism and develop a model to capture this sort of process. So this is the first sort of the understanding of how the internal erosion affects the mechanical behavior of soil specimen. And you can see this is the volumetric strain, derivative strain. This is the very typical behavior of the volumetric strain behavior of a soil specimen without being eroded. You can see this volumetric contraction and then dilation. And then this curve is the behavior of soil specimen under different pre-shearing stress ratio due to internal erosion. There's no mechanical loading, just internal erosion. And you can see that under low pre-shearing stress ratio, the sample undergo contraction. But as you increase the pre-shearing stress ratio, you see the sample being less contracted. So we use this understanding to develop some what we call the erosion dilation model. So when we have a granular sample, we have to apply the mechanical loss. We have a latency model caused by mechanical loss. This is an additional sort of model to describe how erosion causing the volumetric change of the material. You can see that under erosion, the latency behavior of the material depending on the derivative stress. And then the other important components of is the onset of subfusion and subfotion. So when you're looking at the internal erosion, this is the original soil specimen under the action of the hydraulic gradient. You can have mud loss but no deformation. So this is what we call subfusion. But as you have further mud loss, the sample starts to undergo deformation, and this is a subfusion process. So we need to be able to detect when this transition process occurs. So we're using DEM simulation to detect this point. Basically, we plot the volumetric deformation and erodic fraction. And then this is the point where we define the onset of subfusions, basically erosion-induced deformation. And then we plot this statistical data and we were able to establish this what we call subfusion surface. So basically there's no volume change within these domains, and when you're hitting these domains, you start having this sort of the deformation. And we use this to develop the mathematical model. And finally, we have a mechanical behavior and we have the mass load. So we need to link them to describe how the mass load causing the deformation. So again, we're using the DEM and we plot this sort of the gradient of this curve with respect to different stress ratio, and we was able to link this sort of the mass loss with the volumetric deformation of the soil. And this is highly depending on the pre-shearing stress ratio. Now we have only three components actually coming from DEM simulation, micromechanical investigation. Now we need a mathematical model to formulate this. And in our work, we're using the Kaizen Kernstich model. So this is basically the Kernstich framework that we developed to incorporate those of the micromechanical understanding into the Kernstich model. The last component that we need to do is to link, internal erosion causing the change in the grand static erosion. So we need to actually link this of micromechanical erosion to the Kernstich model. And to do this, we borrow the concept of this handsome guy who's actually here, Itai Ainam, the one who actually proposed this of the breakage index. We're using it to formulate erosion index. So this is the Kernstich model that we developed, and I quickly show you how we actually predict the behavior of the sample. So this is the loading process. This is a percent stress ratio. This is the mass loss erosion rate. So what we did here was we pre-share a sample, and then we erode the sample with different amounts of erosion. And you can see that the green one here is the sample without erosions. And then the red one was sample with 5% mass loss and 10% mass loss. So you see that this is pre-sharing, erosion, and then the change in the mechanical behavior due to erosion. So you can, from this you can see that model we were able to capture with increasing in the term of erosion, it actually causing the reduction in the big streams. And similarly, this is the volumetric behavior. The green one is no erosions, and you can see from these predictions, the model was able to tell that with the increase in the mass loss, the sample become more contraction. So this is what we capture from the developed model. In the first couple of slides, I'm also talking about the effect of the high pre-sharing stress ratio and how the high pre-sharing stress ratio cause the unstable of the sample. So here we test the same scenario. You can see the red line here is the simulation with the prediction with relatively low pre-sharing stress ratio, and the blue one with a high pre-sharing stress ratio. So with the blue one, we load the sample to this point, and then we erode the sample, and when it hit to this point, it's collapsed. It's not able to maintain stable. So we was able to capture all of this behavior. Now we have a Kernstich model. And we also verify our model with experiments, and we demonstrate that the Kernstich model was able to capture these experiments reported in the literature. Bearing in mind that in the literature, we don't have the experiments that report influence of pre-sharing stress ratio on the mechanical behavior of the sample. And this is still a challenge in terms of experimental setups. So we have a Kernstich model. Next, we need to have this mathematical model and a computational methods. I will briefly introduce these two concepts and demonstrate the performance of the model. So when we want to model this process at a few boundary value of application and a few scale, you need to have a robust sort of mathematical model. And the key question here is, how do we formulate a continuum model? How many components do we need? So if you're looking at this process here, you can see that for this, you can see that this at RV, you have a cold sand, fine sand. Fluidized sand means the particle, when they actually detect from the soil, they become fluidized particle and they flow with water particle. You have a water phase, and you also have air phase if you're looking at this boundary value application. So because of this, we propose what we call the 5-phase model, and it was conducted by my PhD student project in the CMAME. This is the solution. We have this RVE, we have a coarse glass particle, fine particle. They will actually detect, erode it, become and flow with the water particle, water phase and air phase. So then we using this sort of assumption and adopting the mixture theory to derive the Goldman equation. Basically, what we're doing here is we establish the Goldman equation for each of the homogeneous phases using this of mass and momentum conservation equation. We ignore the effect of the temperature. And then we combine them together to define the sets of Goldman equation that needs to be used, needs to be solved. For example, this equation describes how the porosity change with erosion, how the concentration change, which is basically related to the fluidized soil, how the concentration change with the erosion, how the fine content change, and so on. Now, when you're looking at internal erosion here, one of the most difficult and challenging issue that we have at the moment is the internal erosion law. We don't have a sound theoretical sort of the law that can be used for our global equation. Most of the existing internal erosion law are empirical. So this is something we're also looking at the moment. Now, to solve this equation, we need a numerical tool. In our work, we're using what we call the smooth particle hydrodynamics. It's basically the continuum numerical method that can simulate the formation problem. So I don't have time to go into the detail, but what I can say is SPF is advantage because they have no background mass. You can simulate extremely large deformation problem. The disadvantage is that it actually not easy to use. But the good thing is in our research group we have developed this computational platform which is free to use. So you can actually using this platform if you wish. I have 2 more minutes. I can finish in my presentation. So this is a demonstration which show how all of those model can predict this experiment setup. This is the experimental setup. This is the embankment made by steel sand. You have water inlet from here, so you can see this is the experiment. This is the seepage flows due to this water outlet, and the seepage flow progress toward the toe of the slope embankment. And then what happened here is because of the seepage flow, there's a mud loss occurred in this location. And you can see this is a very complex and challenging problem. You see this sort of the erosion induced the toe collapse, and this sort of the caving shape of failure. Can we describe this sort of process using numerical model? So this is our concept model with some sort of set of parameters, and this is the prediction. This is the 5 contents, statics, this is strain, and that is the pore water pressure. And you can see that we was able to, under the substrate of the seepage flows, the mud loss occurs at the toes, and gradually it actually reduce the strength of material, causing the material to flow with the water, and then causing this failure mechanism. So this is what we was able to simulate this process. And then the final one was we tried to actually using this model to predict what we call backward erosion. So this is the field scale experiment conducted by a group in Netherlands. They create this